Welcome to Science in Minutes, the podcast where cutting-edge research meets clear and curious minds. I'm Dr. Hamdaoui, physicist and researcher, and I'll be your guide through today's scientific deep dive. In each episode, we explore one recent scientific paper in physics, technology, informatics, or mathematics, distilled into just a few minutes. Joining me today is Alice as we unpack a study that challenges something scientists thought was impossible. Can light actually pass through the entire adult human head? And what can that reveal about the brain? You're about to find out.
Okay, so let's dive into this. You know how when we talk about looking into the human brain using light, things like FNIRS, functional near-infrared spectroscopy.
Right. It's that technique using near-infrared light, bouncing it off the head, basically, to see, blood flow changes linked to brain activity.
Exactly. And it's great, cheaper than fMRI, more portable, better spatial detail than EEG sometimes.
But there's always a but, isn't there? There's this huge, fundamental problem anyone using it runs into straight away.
Which is?
Light scattering and absorption, too, of course. Human tissue is just incredibly effective at scattering light. Think shining a light into fog or milk.
It doesn't get very far.
Precisely. The light just bounces around like crazy. So the signal you want, the useful information, it just fades out super quickly as you try to go deeper.
So with standard FNIRS, you're pretty much stuck looking at the surface, right? About, 4 centimeters deep? Mostly just the outer cortex.
Yeah, the outer wrinkles, all that fascinating stuff deep inside the lower cortical folds, thalamus, brainstem, cerebellum. It's just, it's off limits for typical optical methods.
Right, and for ages, the general thinking, almost like a hard rule, was that it was just physically impossible to get light all the way through an adult head.
You mean like source on one temple, detector on the other?
Yeah, straight across.
Absolutely impossible. That was the consensus. Because the estimated attenuation, the light signal dims passing through skin, skull, brain, everything. The numbers were just staggering.
I was staggering, you're talking.
Simple models were throwing around numbers like 10 to the power of 18. That's a 1 with 18 zeros after it.
Whoa.
Yeah. It's like finding one specific grain of sand on all the world's beaches. The signal was just assumed to be completely, utterly swamped by noise.
Yeah, mind-boggling.
Yeah.
So basically, forget about it. Don't even try. But,
yeah.
And here's the really cool part. We've got this new research paper that kind of looked at that impossible idea and went, maybe.
Right. They decided to directly test it. Is it actually physically possible, despite those crazy numbers, to detect photons transmitted right across?
So that's our mission for this deep dive. We're going to unpack this pretty complex paper, figure out how on earth they tackled this, what they actually discovered, and crucially, what this could mean down the road for looking deep inside the brain with light.
Sounds good. Let's get into it.
Okay, so 10 to the 18 attenuation. That's the dragon they're trying to slay.
Yeah.
How do you even begin to approach that? What was the game plan?
Well, they came at it from two angles, really. Sophisticated computer simulations on one hand and really carefully designed experiments on the other.
Okay, simulations first. What kind?
They used Monte Carlo modeling.
Ah, right. That's where you simulate like the random walk of millions or billions of individual photons traveling through a model. Yeah, tracking each bounce, each absorption.
That's the basic idea. They used a very detailed, realistic head model based on MRI scans, sectioned into layers, skin, skull, CSF, gray matter, white matter, each with its own optical properties. And to even have a statistical prayer of simulating a photon making it all the way across this model, they had to simulate an unbelievable number of photons.
So many?
Over 7.24 trillion.
Trillion. With a T.
To the T. Just running the simulations took hundreds of hours on, high-performance computing clusters.
Wow. Okay, so trillions of simulated photons just to see if any might theoretically make it. That really paints a picture of the challenge.
Yeah.
So what about the actual experiment? You can't just use a standard FNIRS setup, presumably.
Oh, absolutely not. The experimental rig was key. They needed to pump in as much light as possible safely and then have an incredibly sensitive detector on the other side.
How did they do that?
They used a pretty powerful pulsed laser, 1.2 watts at 800 nanometers, which is in that useful near-infrared window where tissue is a bit more transparent. But instead of focusing it to a point, they expanded the beam into a circle about an inch across and shone that onto the side of the head.
Huh. Why a big circle when you want it focused?
Normally, maybe. But here, the main goal was just getting enough photons in without burning the skin. Spreading the power over a larger area lets you use higher total power while staying within safety limits.
Okay, that makes sense. Maximize the input safely. What about catching the photons on the other side? Must be like looking for needles in a haystack.
Needles in about 1 billion haystacks. They used a large area, single photon sensitive detector. Think of it like a super camera that can literally count individual photons hitting it. And they coupled that to a special fiber bundle to collect light over an even wider area on the opposite side of the head.
So big source area, big collection area, inject maximum light, collect maximum light, anything else. How do you separate the signal, however tiny, from just random background light?
Yeah, timing. That was absolutely critical. They used something called time-correlated single photon counting, or TCSPC.
Okay.
So the laser sends out these incredibly short pulses of light. The detector is synchronized with the laser. When a photon arrives at the detector, it records its arrival time relative to when the laser pulse was fired.
I see. So photons that actually traveled through the head will arrive after a certain delay?
Exactly, depending on the path they took. By building up a histogram, a chart of these arrival times over many pulses, you can see a bump corresponding to the photons that took the head path. This time gating is crucial for filtering out random noise photons that arrive at the wrong times, essential when your signal is almost non-existent.
Okay, got it. So simulations predicting it's just barely possible, this optimized setup with the big laser, big detector, precise timing, the $1 million question, or maybe the 10 to the $18th question. Did they actually detect photons that crossed an entire adult human head?
They did, yes, seriously.
Uh-huh.
In one specific participant described as an adult male with fair skin and no hair on his head, they clearly and reliably measured a time-correlated signal, photons that had gone right across his head, side to side.
Wow. Okay, so that 10 to the 18 attenuation estimate, was it actually that bad? What did they measure?
It was pretty much spot on. The measured attenuation was indeed right around that order of magnitude, 10 to the 18. The actual signal they detected, once you average it out over the measurement time, was equivalent to about 1 single photon per second, making it through from that 1.2-watt laser source.
1 photon per second. After starting with, well, trillions and trillions per second from the laser.
Yeah.
It's unbelievable. It fundamentally changes things, doesn't it? But you said one specific participant. What about others?
And that's the immediate practical hurdle. They tested 7 other people, different skin tones, hair types, head shapes, and in those individuals, they didn't manage to detect a significant signal above the background noise. The researchers strongly suspect that the first subject's fair skin and lack of hair were critical factors. They absorb and scatter less light, especially near infrared light, giving those few photons a slightly better chance of making it through to be detected by their current setup.
That makes sense. Dark hair and skin absorb more light. So, okay, it is physically possible. They prove the principle. But right now, it's extremely sensitive to individual characteristics. And you mentioned averaged over time. How long do they actually have to sit there collecting data?
Yeah, that's the other catch for note. To build up enough detected photons to get a clear signal in that time-of-flight histogram took about 30 minutes of total acquisition time for each measurement spot. And that was often broken up into multiple shorter trials.
30 minutes. Okay. So if you're thinking about watching brain activity happening in real time, thoughts flashing, responses happening in milliseconds, this isn't it. Not today, anyway.
Definitely not today. It's far too slow for dynamic functional imaging right now. But just proving that any detection is possible across the whole head, that's the breakthrough here.
It really is. It redraws the map of what we thought light could do in the brain. And you mentioned the analysis of how the light got through was also interesting. It wasn't just diffusing randomly.
Right. That's perhaps just as fascinating. You'd intuitively think, wouldn't you, that in such a highly scattering medium, the light would just spread out like a big fuzzy uniform cloud.
Yeah, like light hitting fog just diffuses outwards everywhere.
But the simulations, and crucially the fact that the timing of the detected photons in the experiment matched the simulated timing really well, suggests something more structured is going on, especially over these very long paths.
More structured how?
Well, remember the head model has layers. Skin, skull, CSF, gray matter, white matter. These layers have quite different optical properties, how much they scatter, how much they absorb.
Okay.
So the light doesn't just scatter equally everywhere. The simulations showed that photons taking these super long paths across the head tend to get channeled or guided along pathways of least scattering and absorption.
Guided, like finding little highways through the tissue?
Kind of, yeah. And when you look at the layers, which one stands out as being significantly less scattering and absorbing than, say, dense brain tissue or bone?
the fluid, the
Yeah.
cerebrospinal fluid, the CSF.
Exactly. The CSF, it fills the space between the brain and skull, goes down into the folds. It's much clearer, optically speaking. The simulations clearly show that these transhead light paths were heavily concentrated within these CSF-filled spaces.
Whoa, so the light isn't just brute forcing its way through the densest parts of the brain, it's finding these clearer channels, these CSF layers, and following them. That's a completely different picture.
It really is. Now, the CSF guiding effect isn't totally new. It's known to sometimes contaminate standard FNIRS signals, picking up stuff from the surface layers. But what this paper argues is that for this extreme transhead transmission, this guiding isn't a bug, it's a feature. It might be the only reason any photons make it across at all, and maybe it could be exploited.
Exploited. How do you mean?
Well, the simulations suggested that by carefully choosing where you place the light source and the detector, you might be able to preferentially launch light into and collect light from specific guided pathways.
Oh, like aiming for different CSF channels.
Potentially. They showed that moving the source location could bias the dominant light paths. Sometimes they'd travel more in the CSF around the top of the brain, other times through CSF pathways lower down.
So you could potentially use these natural light pipes to gain sensitivity to different deep brain regions just by optimizing the geometry. That sounds huge.
That's the implication, yes.
Oh.
And their sensitivity analysis, looking at where changes in absorption inside the head would most affect the detected signal, suggested that these transhead measurements are indeed sensitive to changes in deep brain structures. Areas like the midbrain, deep within the sulci, parts of the cerebellum, places previously thought to be completely invisible to optical methods.
That really is a potential game changer then. Okay, it's slow now. It depends a lot on the person's head characteristics.
Yeah.
But the fundamental point is light can get there, interact with deep structures, and a signal can be detected coming out the other side.
It pushes the boundaries. It proves the physical possibility. It's not ready for prime time in the clinic tomorrow for watching rapid brain function, no. But showing you can overcome 10 to the 18 attenuation across a whole head, that's a massive foundational piece of evidence.
Yeah, it really makes you think. I mean, if they manage this incredible feat now, essentially catching 1 photon per second after 30 minutes of collection.
And that's after really optimizing the setup. Strong laser, big areas, super sensitive detectors, that clever timing technique.
Right. But given they conquered that level of attenuation, 10 to the 18, through smart engineering and analysis, what happens when technology improves further? Imagine even faster single photon detectors, maybe one sensitive to different wavelengths.
Exactly, like longer wavelengths in the shortwave infrared spectrum, maybe. They penetrate tissue even better, theoretically. The detectors aren't quite there yet for this kind of counting, but...
But this study shows there is a signal to find, however faint, if the tech gets good enough. So the provocative thought then is, if we can make detecting these incredibly determined, deep-diving photons faster, more reliable, maybe less dependent on things like hair, what completely new windows into the deep brain could that open up? What insights into those hidden regions controlling fundamental processes might we finally gain using light?
It's a really exciting prospect, and a great reminder, isn't it, that sometimes what looks utterly impossible based on current tech or simple models might just be waiting for the right approach, the right experiment.
Absolutely. A truly fascinating deep dive into the surprising journey of light through our own heads.
Thanks for tuning in. You can find the link to the paper below. If you found this episode insightful, don't forget to subscribe, leave a review, or share it with someone curious about biomedical optics and the physics of the brain. Until next time, keep asking questions and stay curious.